Hello dear student, welcome to Vyas Edification. In this session, we are going to discuss NCERT and exercise solutions of class 12 chapter number 2 Electrostatic Potential and Capacitance. In this lecture, you will find detailed solution of each and every question, as well as you will find here some hidden concept also. Clear? So, for detailed solution, concentrate on a screen. So, now dear student, we are going to discuss question number 2.1. In this question, it is given to you two charges 5 into 10 to the power minus 8 coulomb and minus 3 into 10 to the power minus 8 coulomb are located 16 centimeter apart. Clear? So, let's suppose I am taking here, let's suppose this is a line. Clear? And this line is joining center to center of these two charges. Clear? So, let's suppose first charge, let's suppose it is placed at this point and value of this charge is given to you 5 into 10 to the power minus 8 coulomb. Clear? And second charge is given to you, let's suppose this is Q2 and value of this charge is given minus 3 into 10 to the power minus 8 coulomb. Clear? It is located at 16 centimeter apart, means we can say this distance is given, this is 16 centimeter. Clear to everyone? Okay. At what point on the line joining the two charges is electric potential is 0. Clear? So, my dear student, you know what is electric potential. Clear? Electric potential is defined as, let's suppose if we are bringing any test charge or a unit charge from infinity to a certain point, then work done per unit charge, this is known as electric potential at that point. Clear? So, one reference is given to you, take the potential at infinity to be 0. Clear? So, first condition is given to you and we have to find the position of a point where electric potential is 0. Clear? So, let's suppose initially I am taking here 3 points and let us try to understand at which point we can find electric potential is 0. Clear? So, let's suppose we are taking here 3 points. Let's suppose first this is point P, let's suppose this point we have R and let's suppose this is S. Clear? So, we know electric potential is a scalar quantity. Clear? So, directly we can add magnitudes. Clear? So, if we write here electric potential due to a point charge. So, electric potential due to a point charge, this is given by KQ by R. Yes or no? Yes. And what is value of K? Value of K, this is given to you 1 upon 4 pi epsilon naught and this is equal to 9 into 10 to the power 9. Clear? Now, what is unit? Unit we have, this is Newton meter square divided by Coulomb square. Clear to everyone? So, now first our objective here is to find the position where we can find electric potential is 0. Clear? So, now we can say electric potential we can write like due to this positive charge and due to this negative charge. So, if we concentrate on a point P, we can write like this, potential at point P, it will be due to V1 plus V2. Clear? We will find potential due to both the charges. Clear? So, let's suppose I am assuming this distance is x. So, this distance we can write like this 16 minus x. Clear to you? So, we can write like this V1. V1 means what? Potential due to 1. So, we can write like this K Q1 upon and we can say distance is given to you x. Clear? Here we can write like this K Q2 divided by total distance we have 16 minus x. Clear? So, this is value of Vp. Clear? Potential at point P. Clear? Now, so can we find here potential 0? Listen carefully. We can say here Q2 is negative. Yes, and definitely we can find a position where electric potential is 0. So, we can write like this Vp equal to 0. Clear? So, we can say K is common. We can write like this Q1. Q1 value is given to you 5 into 10 to the power minus 8 divide by. Clear? This value is given x. Now, value of Q2. Value of Q2 we have minus 3 into 10 to the power minus 8 and it is divided by 16 minus x. Clear to you? And we can put this is equal to 0. Clear? So, from here we can write like this 5 into 10 to the power minus 8 divided by x, this should be equal to 3 into 10 to the power minus 8 over 16 minus x. clear, because we know K value it cannot be 0. So definitely this bracket term will be 0, clear. So we can write like this one and this one cancel out. So from here we can say 16 minus x upon x, clear, and this should be equal to 3 by 5, clear. So now we can write like this. If we cross multiply, we can say 16 multiply 5, we have 80, 80 minus 5x, clear. So this is 5x, it is equal to, if we multiply x with 3, this is 3x, clear. From here we can say 8x, this should be equal to 80. So value of x we are getting 10 centimeter, clear to you. It means between these two charges, the line joining, on the line joining we can find that from the 10 centimeter from Q1 and from 6 centimeter from Q2, we are getting a point where electric potential is 0, clear. So this is one position. So one position we get here, the x value is 10 centimeter, clear to you? Yes. Now if we concentrate on the rest of 2 points, the point S and point R, clear. So now can we find, first logically, at which point we can find electric potential 0. Now listen carefully. Actually we have formula KQ upon R, yes or no? Now you can see, if we talk about Q1 and Q2, definite in terms of magnitude Q1 is greater, yes or no? This is a minus sign, no doubt. But if we talk about only magnitude, so Q1 is greater and distance from the Q1 is less. It means both the factors are increasing potential at point R due to Q1, yes or no? It means we can say here we will not find potential 0 at point R, clear. It means we can say to the left side of Q1 we will not find electric potential 0, yes or no, clear. Okay. So now if we concentrate on point S, clear, at point S you can see this magnitude is having a larger distance from point S, clear. It means we can say magnitude is more, distance is also more. It means we can find, we may be find Q by R ratio such that electric potential it may be 0, yes. So let's suppose if we talk about S, so we can say, let's suppose I am taking this distance is x, clear. So what is distance from Q2? We can say this is x minus 16, or we can say this is 16 minus x, clear. This is 16 minus x, clear everyone. So now we can write like this, Vs, this should be equal to 0, and we can say this is kq1 upon x plus we can say kq2 upon 16 minus x, sorry, x minus 16, sorry, this is x minus 16, clear. So we can write like this is x minus 16, clear to everyone. Now we will put this is equal to 0, clear. So now if we put all the values, how can we write? Yes. So if we put here this value 0, we can say if we take k common, value of Q1 we have 5 into 10 to the power minus 8, 5 into 10 to the power minus 8 divided by, we can say value x, so we can say this is x, clear. Here we can write plus Q2 value we have minus 3 into 10 to the power minus 8, so minus 3 into 10 to the power minus 8 and it is divided by, we can say this is x minus 16, so x minus 16 and this should be equal to 0, clear. So from here we can say 5 into 10 to the power minus 8 divided by x, this should be equal to 3 into 10 to the power minus 8 upon x minus 16, clear. So from here we can say this one and this one cancelled out, clear. So we can write like this, x minus 16 upon x, this should be equal to 3 by 5, clear. So if we cross multiply, we can write like this, 5x minus 80, this should be equal to 3x, clear. So we can write like this, 2x, this is equal to 80, so value of x we have 40 centimeter, clear to you. It means in this question we are getting two positions where electric potential may be 0. Number one position is at a distance 10 centimeter from Q1 and second position we are getting x equal to 40 centimeter from Q1, clear to you. Yes, and if it say what is distance from Q2, so 40 centimeter from here, we can say 40 minus 16, it means 24 centimeter from Q2, clear. So like this you can calculate positions where we can find electric potential 0, clear. Now dear student, we are going to discuss question number 2.2. In this question it is given a regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices, okay. Calculate the potential at the center of hexagon, clear. So now concentrate. Let's suppose first if we draw here a regular hexagon, so let's suppose this is hexagon, this one, clear. This is regular hexagon and we are placing charge 5 microcoulomb at its vertices. So let's suppose we are placing charges at this point, this one, clear, and charge is given to you, this is 5 microcoulomb. So 5 microcoulomb charge, here we also have 5 microcoulomb, 5 microcoulomb, 5 microcoulomb, and this one is also 5 microcoulomb, clear. In this question given, because this is regular hexagon, it means side is same, clear. So we can say this distance is given to you 10 centimeter, clear to you, okay. So we have to calculate potential at the center of hexagon, clear. So if we join these charges like this, now you can see actually we will find center at this point, clear. Now listen carefully, if this is a regular hexagon, clear, if this is regular hexagon, we can say this angle is what, 60, clear, this angle is also 60, this is also 60, yes or no. It means we can say if this side is 10 centimeter, it means we can say this can form equilateral triangle, yes. So we can say this is also 10, this is also 10, clear. So if it say distance of center from each charge we are getting 10 centimeter, yes or no, okay. Now our objective here is to calculate potential at point O due to all the charges, clear. Now you can see from each charge we are getting center point at the same distance and value of charge is also same. So can we write like this, V equal to 6 times of K Q by R, yes or no. What I am saying to you, actually we have 6 charge, so if we calculate potential due to one charge, if we multiply it with 6, we will find total value of electric potential at center O, clear. So we can write like this, V, this should be equal to 6 multiply value of K we have 9 into 10 to the power 9 into value of Q, this is given 5 into 10 to the power minus 6, clear, and it is divided by value of R is given 10 centimeter. So we can say this is 10 into 10 to the power minus 2, clear. So we can write like this, 6 into 9 into 5 into 10 to the power 3 divided by 10 to the power minus 1, clear. So we can say this is equal to 6 into 9 into 5 into 10 to the power 4 and this is volt, yes or no. So if you multiply, we can write like this, this is 30 into 9 into 10 to the power 4, or we can say this is 270 into 10 to the power 4 volt, clear. So from here we can see value of V, this is given by 2.7 into 10 to the power 6 volt, clear to you. So we can say electric potential at center of this regular hexagon we are getting 2.7 into 10 to the power 6 volt, clear to everyone. Now dear student, we are going to discuss question number 2.3, and in this question it is given to you two charges 2 microcoulomb and minus 2 microcoulomb are placed at point A and B 6 centimeter apart, clear. So we can write like this, let's suppose this is point A, clear, and let's suppose here we have point P, clear. Distance between A and B, it is given to you 6 centimeter, clear to everyone, okay. Two charges 2 microcoulomb and minus 2 microcoulomb is placed, so we can write this is 2 microcoulomb, this is minus 2 microcoulomb, clear to you. Now it is given here in this question, identify an equipotential surface of an system. So first of all, let us try to understand what is equipotential surface. Equipotential is the surface at which we will find net electric potential is 0, yes or no. So now we can say where we can find electric potential 0. Now actually we know we can find whenever we have two opposite charges we find electric potential 0 at either in between A and B or to the right side of a negative charge, or we can say a less charge, clear. But you can say magnitude wise both the charges is same, clear. So definitely we find electric potential at a midpoint, this is 0, clear. So let's suppose I am taking this point is P, let's suppose this distance is x and this is also x, clear. Total we can say x equal to 3 centimeter, clear. So we can say potential at P we can write like this is VA plus VB, clear. Potential due to A we can say this is K, this is 2 microcoulomb divided by x, plus we can also write like this K minus 2 microcoulomb divided by x. Now we can say this one and this one cancelled out, clear. So from here we can say we are getting electric potential at point P, this is 0, clear to everyone, yes or no. So it means we can say we are getting a P point where we will find electric potential 0, clear. But we have to identify an equipotential surface of a system, clear. So how can we find a equipotential surface? Listen carefully. So now you know this is point A and B and this is position where we have electric potential 0, clear. Let's suppose if I concentrate on this point, clear, and let's suppose this point is located at a distance r from this A and let's suppose from r, clear. Now we can say again we are having the magnitude wise charge is same and the distance is also same. It means we can say here again we will find net electric potential 0 because electric potential is a scalar quantity, we will direct add it, yes. It means we can say all those points which like this where we will find electric potential 0, yes or no. So from here you can see electric potential surface, it will be like this, clear to you. This will be electric potential surface and we can say this is equipotential surface according to part number A, clear to everyone, yes or no. Now the next question is here, what is the direction of electric field at every point on the surface? Now listen carefully. If we talk about direction, at point P we can say this is positive charge, due to this charge electric field in this direction, and due to this negative charge we can say electric field in this direction. So we can say this is EA and BB and direction of electric field is always from A to B, clear. Let's suppose if you say sir what will happen if we talk about this point, clear. So we can say direction is given by like this due to EA, clear. Here we can say direction is given by EB like this, yes or no. So if we talk about resultant, we always find resultant in this direction, clear. So if we talk about at any point, you always find electric field direction from A to B, clear. Let's suppose if you say sir what about this point, so on this point we can say electric field in this direction due to A, due to B we can say electric field in this direction, this is EB. So if we find net resultant electric field, it will be in this direction, yes or no. So you always find electric field direction in right from A to B, clear to you. So this is the question number B, clear. So this is all about this solution. Now dear student, we are going to discuss next question, question number 2.4, and in this question it is given to you a spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 to the power minus 7 coulomb distributed uniformly on its surface, clear. What is electric field inside the sphere, just outside the sphere, and at a point 18 centimeter from center of sphere, clear to everyone. So now concentrate on a screen. So in this question it is given to you, we have a spherical conductor. So we have a spherical conductor, so this is spherical conductor, clear, of radius 12 centimeter. So we can say radius of this conductor we have, this is 12 centimeter, clear. It has a charge of 1.6 into 10 to the power minus 7 coulomb, clear. So charge this is given to you 1.6 10 to the power minus 7 coulomb, clear. It distributed uniformly on its surface because it is written here spherical conductor. Always keep in mind, if it is written spherical conductor, it means whatever charge you are providing on a sphere, it will equally distributed on the surface, yes or no. So it is given. Now what is electric field? Electric field number 1 inside a sphere, clear. Now if we talk about, let's suppose if we are taking here 3 points, let's suppose this is point A, let's suppose I am taking this is point B, and here we have point C, clear. So if we talk about this point A, let's suppose this is small r, clear. So we can say when r is less than capital R, clear, when r is less than capital R. Now we can say whenever we have a spherical conductor, electric field inside is always 0, because if we take here a Gaussian surface, so in the Gaussian surface, let's suppose if you assume any Gaussian surface, this one, so within this Gaussian surface you will not find any electric charge, clear. So we can say electric field is 0, yes or no. So electric field is 0, it means first answer of this question we have electric field inside sphere we are getting 0, yes or no, clear. Second part, it is given just outside the sphere. Just outside the sphere means approximately we are talking about at point B, clear. So we can say electric field at B, this is given by KQ by R square, clear. Value of K we have 9 into 10 to the power 9 into value of charge Q, this is given 1.6 into 10 to the power minus 7 and divided by R square. Value of R, this is given 12 centimeter. So 12 into 12 into 10 to the power minus 4, clear. From here we can see, if we write here this is 10, we can say this is 3, this is 4 and we can say this is 3, clear. This one and this one cancelled out, clear. So from here we can say value of AB, this is given by 10 to the power 9 into 10 to the power minus 7. So this is 10 to the power 2 divided by, we can say 10 to the power minus 3, clear. So from here you can say this is 10 to the power 5 and what is unit of electric field? This is Newton per Coulomb, yes or no. So this is value of electric field just outside the sphere, clear. Now in part number C, question is at a point 18 centimeter from center of sphere, clear. So at a point 18 centimeter from center of sphere, so we can write like this part C, 18 centimeter, 18 centimeter, it means we are talking about point C, yes or no, because radius is given 12 centimeter and objective is 18 centimeter. So now we can write like this, electric field at point C, clear. We can treat this sphere as a point charge, or we can assume all the charge is concentrated on center, clear. So we can say this is KQ upon small r square, yes or no. Now we can write like this, value of K we have 9 into 10 to the power 9 into value of Q, this is given 1.6 into 10 to the power minus 7, clear, and divided by R square. Value of R is given 18 centimeter. So this is 18 into 18 into 10 to the power minus 4, clear to you, yes. So now we can write like this, EC value, EC is given by, clear, we can say if we remove this decimal, this is what 10, clear. We can say this is what 2, we can say this is 8, clear. So now we can write like this, 8 into 10 to the power 2 divided by, clear, we can see 18 into 10 to the power minus 3, clear. From here you can say 9, we can write like this, this is 4 divided by 9 into 10 to the power 5, clear. So if you write like this, this is 40 by 9 into 10 to the power 4, or we can say this is approximately, we can say 4 point, here we have 4 left, 4.4 into 10 to the power 4 and this is Newton per Coulomb, clear. So this is value of electric field at a distance 18 centimeter from center of sphere, clear. So this is all about solution of this question. Now dear student, we are going to discuss question number 2.5, and in this question it is given to you a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. What will be capacitance if distance between plate is reduced by half and space between them is filled with the substance of dielectric constant K, clear. So now let us try to understand given situation. In this situation it is given we have a parallel plate capacitor. So let's suppose this is a parallel plate capacitor, clear, and it is having air. So between these plates we have air, okay. So it has a capacitance value 8 picofarad. So actually we know for the parallel plate capacitor, value of capacitance is given by epsilon naught A by D, clear, and this value we can say it is equal to 8 picofarad, clear. Now in next situation what is happening, distance between plate is reduced by half. So let's suppose here we have first distance D, then we can say in second situation we are having this distance D by 2, clear to you, and it is also given space between them is filled with dielectric constant 6. So we can say value of K we have here, this is 6. Clear? Yes or no? So now we can say whenever we fill any parallel plate capacitor with any dielectric substance, then we can say its capacitance is increased by K times. Yes or no? So we can say now we can write like this, K epsilon naught A by, and distance between these two plates is reduced by half. So we can say this is D by 2. Clear to you? So from here we can write like this, C dash. This C dash is equal to what? This is equal to twice K and epsilon naught A by, this is D. Clear? Epsilon naught A by D. So epsilon naught A by D, it is equal to C, and C is equal to 8 picofarad. So we can say C dash, this is given by 2K and 8 picofarad. Clear to you? So from here we can write like this, 16 into K, value of K we have 6. So we can say 6. Clear? And we can say this is picofarad. So this is 96 picofarad. Clear? So value of capacitance now become 96 picofarad. Clear? Sometimes the question may be asked like this, what is the ratio of C dash by C? Clear? So definitely you can say this is 12 times, 16 times. Yes or no? Yes or no? So we can write like this, this is 2 multiply 8, here we have, and this is 8 picofarad. Clear? K value is given to you, this is 6. Clear? So directly we can say here C dash over C, this is equal to 12. Clear? So here we will find 12. Clear? But this is the next step. Clear? Correct answer of this question we have 96 picofarad. Clear to everyone? Now dear student, we are going to discuss question number 2.6, and in this question we will discuss about combination of capacitors. Actually we know we have two types of combination, series combination and parallel combination. In series combination, charge on each plate of a capacitor remains same, but voltage is actually divided, or we can say V becomes V1 plus V2 plus V3. But in parallel combination we know potential difference across each plate of a capacitor remains same, but what will happen with the charge? Charge is divided, Q equal to Q1 plus Q2 plus Q3. Clear? So now we are going to discuss this question. 3 capacitors, each of capacitance are connected in series. Clear? So concentrate on a screen. We can say, let's suppose here we have a capacitor, let's suppose here we have a capacitor, and let's suppose here we have a capacitor. Clear? We have total 3 capacitor. Clear? And having capacitance, this is given to you 9 microfarad. Clear? Each capacitor is having same value of capacitance. Clear? What is total capacitance of combination? Clear? So now we know in series combination value of Q remains same, but what about V? So we can say V is given by V1 plus V2 plus V3. Clear? Now let's suppose if we replace this combination by a single capacitor. Clear? And let's suppose equivalent capacitance, let's suppose I am giving with CS. Clear? So we can write like this, this is V equal to what? We can write this is Q by CS. Clear? This is Q by C1 plus Q by C2 plus Q by C3. Clear? From here we can write like this, 1 upon CS, this is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. My dear student, here we have a very easy concept to learn this formula. Actually students are always student can relate this expression with the resistance. Clear? In resistance we always find R equal to R1 plus R2 plus R3 in series, but in capacitor this becomes opposite. Clear? It means in parallel combination of resistance we find 1 upon R equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Here we are getting that combination in series. Clear? So we have just opposite. Yes. So in series combination we are having 1 upon CS equal to this one. Now we can put here values, 1 upon CS equal to 1 upon value of C1. Value of C1 we have, this is 9 microfarad, 1 plus 9, 1 plus 9 plus 1 plus 9. Clear? This should be equal to 3 by 9. Clear? So we can say value of CS, this is given by 9 by 3. Clear? And from here we can say this is equal to 3 microfarad. Clear to you? So what is total capacitance of a combination? Answer, we have 3 microfarad. Clear? Now next question is asking to you, what is potential difference across each capacitor if combination is connected to a 120 volt supply? So we can do one thing, this value we are getting 3 microfarad, and we can say this is connected with the battery, and battery is having potential difference 120 volt, clear. So we can see this is connected with the battery, clear. This is 120 volt, clear to you. So can we find here value of Q? Yes or no? Yes, we can write like this: Q equal to Cs into V. This is 120 into 3 into 10 to the power minus 6, and we can say this is coulomb, clear. From here you can say this is equal to 360 into 10 to the power minus 6 coulomb, clear. Now this is value of a charge, this is present on this capacitor, value of charge remains same. So now we can easily get value of V1, V2 and V3, clear. So now you can write like this: V1 value we have Q1 upon C1. Q value is given 360 into 10 to the power minus 6, 10 to the power minus 6 over value of C1, this is 9 microfarad, so 9 into 10 to the power minus 6, clear. So we can say this is equal to what, 40, so we can say this is 40 volt. Now listen carefully, each capacitor is having same capacitance and it is the value of charge is also same. It means V1, V2, V3 this remains same, V1, V2, V3, and this is equal to 40 volt, clear to everyone? Yes or no? So this is all about this question. Now dear student, we are going to discuss question number 2.7, and in this question it is given to you 3 capacitors of capacitance 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel, clear. What is total capacitance of combination, and we have to determine charge on each capacitor when it is connected with 100 volt supply. Yes, so now concentrate. In this question it is given to you, we have 3 capacitors are connected in parallel. So let's suppose this is one capacitor, clear. We have another capacitor, this one, clear, this one, clear. So we have here 3 capacitors, this is 2 picofarad, this is 3 picofarad, and here we have 4 picofarad, it is connected in parallel combination, clear. What is total capacitance of combination? What is total capacitance of combination, clear. So now we can say these are connected in a parallel, yes or no, and let's suppose it is connected with a battery, clear. It is given in this question, this is 100 volt. So let's suppose charge Q is coming from this side, so we can say let's suppose charge Q1 is going in this one, Q2 and Q3, clear, and here again we are getting total charge Q, clear. So we can say, we can write like this: Q equal to Q1 plus Q2 plus Q3, clear. Now we know in parallel combination potential difference between parallel plate capacitor always remains same. So we can write like this: let's suppose equivalent capacitance is Cp. So Cp V, this should be equal to C1V plus C2V plus C3V, clear. Now we can say V is cancelled out, and value of Cp, this is given C1 plus C2 plus C3, clear to everyone. So Cp equal to this one. Now what is value given? 2, 3, 4. So we can say 2 plus 3 plus 4, this is equal to 9, and this is picofarad, clear. So this is answer of first part. Second part is given: determine charge on each capacitor. Okay, it means now we will find value of C1V, C2V and C3V, clear. So we can write like this: charge on each capacitor. Just a minute. Now we can say charge on each capacitor means Q1 equal to C1 into V. C1 value given 2 picofarad, so 2 into 10 to the power minus 12, and value of V is given, this is 100, yes or no. So from here you can say 2 into 10 to the power minus 10, and this is coulomb, clear. Similarly we can find value of Q2, this is equal to C2 into V, so C2 into V, clear. So we can say value of C2, this is 3 picofarad, so 3 into 10 to the power minus 12 into, this is 100, so 3 into 10 to the power minus 10 coulomb, clear. Now we have third one, this is Q3. So how can we find value of Q3? Q3 is given by, we can say C3 into V, clear. C3 is given, this is 4 picofarad, so 4 into 10 to the power minus 12 into V, clear. V value is given 100 volt, so we can say this is 100, clear. From here we can say this is 400 into 10 to the power minus 12 or 4 into 10 to the power minus 10 coulomb. Clear to you? So like this we can calculate total charge present on a parallel plate capacitor Q1, Q2 and Q3. Clear to everyone? Now dear student, we are going to discuss question number 2.8, and this is again a question related to parallel plate capacitor. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 to the power minus 3 meter square and distance between the plate is given to you 3 mm. Clear? Calculate the capacitance of a capacitor if capacitor is connected to a 100 volt supply and what is charge on each plate of capacitor. Clear? Now concentrate on a screen. Now listen carefully. A parallel plate capacitor is given to you and area of parallel plate capacitor 6 into 10 to the power minus 3 meter square. This is given to you. Clear? And the distance between plate means value of D is given 3 mm. Clear? Yes or no? So now our objective here is to calculate capacitance of a capacitor. So when we fill air between parallel plate capacitor, we can write like this: epsilon naught A by D. Clear? So we can see epsilon naught, this is 8.85 into 10 to the power minus 12, value of area 6 into 10 to the power minus 3, and it is divided by distance between parallel plate 3 mm. So 3 into 10 to the power minus 3. Yes or no? 3 into 10 to the power minus 3. Clear? So now we can see this one and this one cancel out. Here we have 2. So if we multiply it with 2, we can say this is 0. We have 1. This is 7. We have 1, and we can say this is 5 2. This is 10. We have 1. 16 1 17. We have 1. This is 17. Yes. And we can say this is multiplied with 10 to the power minus 12. Clear? So this is value of capacitance. So we can say value of capacitance is given by 17 into 7, 17.7 into 10 to the power minus 12 farad. Clear? Or you can say this is 17.7 pico farad. Clear to everyone? Clear? So this is value of capacitance. Clear? But one more thing is given to you. If we connect this capacitor with 100 volt supply, what is charge? So charge is given by CV. Clear? C value is given 17.7. So 17.7 into 10 to the power minus 12 into voltage is given to you 100. So we can write like this 100. So this is equal to 17.7 into 10 to the power minus 10 coulomb. Clear to you? So this is the answer of this question. Now dear student, we are going to discuss question number 2.9. And in this question it is given to you, explain what would happen if capacitor given in exercise 2.8 a 3 mm thick mica sheet of dielectric constant 6 were inserted between the plates. Clear? So now dear student, first we will take values of next previous question. So it is given to you, area is given 6 into 10 to the power minus 3. Clear? And supply is given to you 100 volt. So we can write like this: area, this is 6 into 10 to the power minus 3 meter square, and voltage is given to you 100 volt. Clear? Okay. And distance between plate is also given to you, this is 3 mm in previous question. Clear? So can we calculate value of capacitance again? Yes. C is given by epsilon naught A by D. Clear? Epsilon naught we have 8.85 into 10 to the power minus 12 multiply area. Area is given 6 into 10 to the power minus 3 divided by value of D. Value of D, this is 3 into 10 to the power minus 3. This one and this one cancelled out, and this is 2 times. Clear? From here you can say this is 17.7 into 10 to the power minus 12. We can say because this is a capacitance, so this is farad. Yes or no? So this is value of capacitance. Now in this question it is given, if we insert a mica sheet having thickness 3 mm between parallel plate capacitor. So now you can say, let's suppose this is a parallel plate capacitor. We introduce here a thick mica sheet and this is 3 mm. This is given to you. Clear? So what will happen when we introduce it? And in part number A, if we discuss part number A, voltage supply remain connected. Listen carefully. So when voltage supply remain connected, it means we can say potential difference across this plate that does not change it, and what will having effect on a charge or capacitance. So we can say C dash, because dielectric inserted, so this becomes K times of C. Yes, value of K is given to you 6. So 6 into 17.7 into 10 to the power minus 12. Clear? From here if you multiply, you can say we have 2, 4, we have 6 and we have 4. So we can say this is 106.2, clear, into 10 to the power minus 12 and this is farad. Clear? So new value of capacitance becomes this much amount. Clear to you? Okay. Now this is value of Q, but is there any change in the value of charge on a parallel plate capacitor? Yes. We can say Q dash, this is equal to C dash into V. Yes or no? Value of C dash now becomes 106.2 into 10 to the power minus 12 multiply 100. Clear to you? Clear? So we can see this is equal to 106.2 into 10 to the power minus 10 coulomb. Clear? It means we can say when this battery remain connected, potential remains same, but value of capacitance increases and value of charge, this is also increases. Clear to everyone? Yes or no? Yes. Now what will happen when supply is disconnected? It means this is for the part A. Clear? Now we are going to discuss part number B. So for part B, now what we are doing, we are disconnecting this supply. Clear? At the time you can say if we insert any dielectric plate between parallel plate capacitor, we can say its capacitance increases. Yes, its value becomes this one. Clear to you? And what about the charges? Because we have already disconnected a battery, it means charge on this parallel plate capacitor, this remains same. Why? Because we can say this plate actually behaves just like an isolated plate. Clear? So we can say value of charge remains same, but what will happen on a potential? Yes. Now you can say whenever we insert a dielectric slab between parallel plate capacitor, electric field, net electric field decreases. Yes or no? Or we can say E dash equal to E by K. Clear? And we know there is a relation between electric field and potential difference. So we can also write like this, V dash equal to V by K. It means we can say potential difference is decreases by K times. Clear? It means we can say this is 100 by 6. So we can say this is 16.66 volt. Clear? So we can say now final potential difference, this becomes 16.66 volt. Clear to everyone? So this is all about this question. Clear? Now dear student, we are going to discuss next question, question number 2.10, and in this question it is given a 12 picofarad capacitor is connected to a 50 volt battery. Okay, how much electrostatic energy is stored in a capacitor? So dear student, this is just a formula based question, and we know electric energy, or we can say electrostatic energy stored in a capacitor, this is indicated by U and this is given by half of CV square. Clear? Where C is what? Capacitance. Clear? And V is potential difference. So value of capacitance is given to you 12 picofarad. So 12 into 10 to the power minus 12 multiplied. We can say potential difference. So this is 50 whole square. Clear? So you can easily calculate 6 into 10 to the power minus 12 into, we can say this is 2500. Clear? So from here we can say this is 150 into 100 into 10 to the power minus 12. Clear? So from here you can say this is 150 into 10 to the power minus 10 joule. Clear? Or you can also write like this, 1.50 into we can say 10 to the power minus 8 joule. Clear to you? Yes or no? So like this you can calculate value of electrostatic energy stored in a capacitor. Actually we have here three different forms of electric energy stored in a capacitor. It is given by half of CV square. We can also write like this, this is Q square divided by 2C, and we can also write like this, this is half of QV. Clear to you? Yes or no? So this is the formula you should keep in your mind. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 2.11, and in this question it is given a 600 picofarad capacitor is charged by a 200 volt supply. Clear? So whenever you find such a question, first draw a circuit diagram like this. A capacitor is connected with a battery and this battery is having potential difference. This is 200 volt and this is 600 picofarad. Clear? And my dear student, this question is very important because this question is generally asked in competitive examinations like JEE Main, NEET. Clear? And this is also important in board examinations. Clear? So now concentrate. So a 600 picofarad capacitor is charged by 200 volt supply. Okay, it is then disconnected from a supply and connected to uncharged 600 picofarad capacitor. So now we can say, let's suppose this is a charged capacitor and this is uncharged capacitor. This is given to you 600 picofarad, this is also 600 picofarad. Clear to you? Okay. Now what is concept here? So first we will find total charge that is present on this parallel plate capacitor. So let's suppose this is Q1. Q1 is given by, this is C into V. C value is given, this is 600 into 10 to the power minus 12 into V is given to you this one, and we can say this value of Q1 we have in coulomb. Yes or no? So now we can find here value of Q2. Now you can say here we have two capacitors and both are connected in parallel. So let's suppose this value we have C1, this is C2. So C1 and C2 are connected in parallel, equivalent we can write like this, C1 plus C2. Clear? C1 plus C2. So we can write like this, C1 plus C2, and this is multiply. Let's suppose we have common potential across this parallel plate capacitor, this is V. Clear? So now we can say this is V. Actually you can also see, because both are connected in a parallel, potential difference remains same. Clear? Now we can say if we talk about this system, so total charge on this system, it always remains same. Yes or no? So we can write like this, this 600 into 10 to the power minus 12 into 200, this should be equal to C1 plus C2. We can say this is 1200 into pico, means 10 to the power minus 12 into V. Clear? From here you can say this one and this one cancel out, this is 2. So from here we can say V is given by 100 volt. Clear? Now our objective in this question is to calculate lost electrostatic energy. Clear? For that one, first we find initial energy. Initial energy is given by half of CV square. C is given to you 600 picofarad. Clear? And V square, V is given 200 square. So we can write like this, 4 into 10 to the power 4. Clear? From here we can say this is 2. So this becomes 1200 into 10 to the power minus 8. Clear? From here you can say this is 12 into 10 to the power minus 6 joule. So this is initial electrostatic energy in a capacitor. Clear? Now we will calculate here final potential, final electrostatic energy. Clear? So final electrostatic energy we can write like this, U final. This is 1 by 2 C1 plus C2 into V square. Clear? So 1 by 2 C1 plus C2. This is given to you, equivalent we have 1200. So 1200 picofarad means 10 to the power minus 12 into value of V. Value of V is given to you, this is 100. We have already calculated common potential, this is 100. Clear? So we can write like this, 100 square means 10 to the power 4. Clear? We can say this is 600 into 10 to the power minus 8. Clear? Or we can say 6 into 10 to the power minus 6 joule. So now we can say initial energy we have 12 into 10 to the power minus 6. Final potential energy, final electrostatic energy we have 6 into 10 to the power minus 6. So now you can say, sir, where is the energy is lost? Clear? And if energy is lost, what will happen here? Actually whenever we inserted a dielectric, half of the energy is stored in between the parallel plate capacitor and half energy is actually utilized to do some work to attract that parallel plate capacitor inside a parallel plate capacitor. Yes or no? And that extra energy it is provided by a battery. Clear? So now we can calculate total lost in energy. This is U initial minus U final. Clear? U initial is given to you. This is 12 into 10 to the power minus 6 minus 6 into 10 to the power minus 6. Clear? So we can write like this, total lost in electrostatic energy, this is given by 6 into 10 to the power minus 6 joule. Clear? So this is all about solution of this question. Clear? Now dear student, we are going to discuss this question number 2.12, and in this question it is given to you, a charge of 8 millicoulomb is located at the origin. Calculate the work done in taking a small charge of minus 2 into 10 to the power minus 9 coulomb from a point P to a point Q via a point R. Clear? So now concentrate on a screen. So we can say, let's suppose this is what Z axis. I am taking, let's suppose I am taking this as Z axis. Let's suppose this is Y axis, and let's suppose this is X axis. Now it is given in this question, a charge is located at an origin. So let's suppose here we have a charge and this value is given to you at millicoulomb. Clear? It is located at origin. Calculate work done in taking a small charge from a point P. Point P is given to you here. This is 0, 0, 3. Clear? So this is point P. Point P to a point Q. Point Q is given 0, 4, 0. Clear? It is given to you via a point R. Clear? So let's suppose R is here. This point is R 0, 6, 9. Clear? So from here you can see, actually we can draw like this. This point is, let's suppose, here. Clear? Now you can see the particle, or we can say calculate work done as small charge. Let's suppose a small charge first going from here to here and then coming to this point. Clear? So this is the path that is given to you. Clear? Our objective here is to calculate total work done if we are bringing a small charge from P to Q. Clear? So my dear student, if you know what is the concept of a potential, electric potential, and how can we define numerically electric potential, listen carefully. So let's suppose here we have a point A. Let's suppose this is a point B. Clear? Let's suppose we are bringing any charge from B to Q, B to A. Clear? If we are bringing any test charge from B to A, we can write potential like this: VA minus VB. This is equal to net work done from B to A divided by that test charge Q. Yes or no? So this concept we will utilize here. Clear? Now listen carefully. We are bringing any small charge from P to Q. Clear? P to Q. So we can write like this: final we have VQ, initial we have VP. Clear? Because we are bringing P to Q, so we write VQ minus VP, and we are bringing the small charge from P to Q and divided by small charge Q. Yes or no? So we have to calculate work done in taking a small charge. Clear? From this is given to you. Clear? This is a value of Q, this one. Clear? So I am taking this is a Q naught because this is a test charge. Clear? Now actually here we have one concept: the total work done, it does not depends on a path. It depends only on the final and the initial position. Clear to you? So how can we write? We can write here WPQ. This should be equal to Q naught. This is VQ minus VP. Clear? Value of Q naught is given to you minus 2 into 10 to the power minus 9 coulomb. Value of potential at Q. Potential at Q due to this charge, it is given by, we can write K, we can say KQ by R. R is given to you better in centimeter. Yes or no? So we can write like this because in centimeter we have, so 4 into 10 to the power minus 2. Clear? Minus VP, potential at point P. We can write like this: KQ divided by, this is 3 centimeters, so 3 into 10 to the power minus 2. Clear? Just we have to do some calculation and we will get our answer. If we take here common 10 to the power minus 2, it will be cancelled out here. So 2 into 10 to the power minus 7 K, we can take K also common. Clear? Or Q also common. So 9 into 10 to the power 9, value of Q 8 millicoulomb. So 8 into 10 to the power minus 3. Now here we have left 1 by 4 minus 1 by 3. Clear? Now just we have to do some calculation and we will get total work done. Yes or no? Yes. So we can write work done from P to Q. This is given by 9 multiplied 2 we have, or you can write like this: minus 2 into 9 into 8. Clear? 10 to the power minus 7, 10 to the power minus 3 minus 10. This is 10 to the power minus 1, 10 to the power minus 1. Clear? Now if we take here LCM, we can see this is 12. Clear? We can say this is 3 minus 4. Clear? So this is minus 1 by 12. Clear? So we can see minus minus plus 2 by 12 into 9 into 8 into 10 to the power minus 1. Clear? Yes or no? So we can write like this: this is 6, we can say this is 2, this is 3 and this is 4. So from here we can say we are getting answer 1.2 joule. Clear? So total amount of work is to be done if we are bringing this charge from point P to Q. This is equal to 1.2 joule. Clear to everyone? Yes or no? Now dear student, we are going to discuss next question 2.13. In this question it is given to you: a cube of side B has a charge Q at each of its vertices. Determine the potential and electric field due to this charge array at the center of a cube. Clear? So now dear student, concentrate on a screen. Now let's suppose here we have a cube. Let's suppose this is cube. Let's suppose this is cube, clear, and here we have a charge, this is placed at the corner of this cube like this, clear, this one and this one, clear. Value of charge is given to you, this is q, and each side is given to you b. Our objective in this question is to calculate electric potential and electric field at center of a cube. So let's suppose this is center of a cube. So if we join this end, it will be look like this, clear. You can say actually this is a diagonal of this cube. So can we calculate? Yes. This is b, we can say this distance is also b. So we can first find this diagonal, this is equal to under root 2b, because this b and b is perpendicular to each other, clear, because this is 3D figure, that's why it is not looking like 90 degree, but this b and this b is perpendicular to each other. So this is under root 2b and this is also b, clear. So can we calculate this diagonal? Yes. We can apply here Pythagoras theorem, b square plus 2b square, this is 3b square, so we can write this is under root of 3b, clear. So distance of this center from each charge, this is given by r, this is equal to under root 3b by 2, clear to everyone. So first of all, if we talk about electric field due to all the charges at the center, how can we see? Listen carefully. Now let's suppose if I say what is electric field due to this charge, let's suppose 1 on this center, definitely we can say in this direction this is E1, clear. Due to this charge, let's suppose this is 2, we can say electric field in this direction, this is E2. Now you can say charge is same, distance is also same, it means we can say we will get here magnitude of electric field, this is also same, and this magnitude is cancelled out by this charge and this charge, yes or no. Same we can say for the other charges also, it means we can say at the center we will find net electric field, this is equal to 0 Newton per Coulomb, clear to everyone, yes or no. And now we are going to discuss about potential, clear. So potential, if we talk about potential, so potential means we can say this is VO, clear. VO is we can say this is equal to, actually we have total number of charges 8, yes, so we can say this is 8 times of V1, clear. So we can say this is 8 into, we can write like this KQ by R, clear. So now we can say 8 into 1 upon 4 pi epsilon naught, value of Q we have Q, and R is given, this is under root of 3b by 2, clear. From here we can say this is 2, clear, and this is equal to 4. So from here we can write like this 4Q divided by under root 3 pi epsilon naught b, clear. So this is value of electric potential at the center, clear to everyone, because Q value is same, R value is same, electric potential is a scalar quantity, it always added, so we do not need to take care of direction, clear. So this is all about the solution of this question, clear.